April 19, 1861, U.S. Arsenal at Harper's Ferry, Virginia. Confederate forces under Colonel Thomas Jackson swept through the Federal armory, seizing 15,000 rifle muskets, crates of ammunition and machinery valued at hundreds of thousands of dollars. The haul seemed like a strategic windfall. Virginia had seceded just 2 days earlier, and the Confederacy desperately needed weapons for an army that barely existed. But within weeks, Confederate ordnance officers discovered a crippling problem. The rifles didn't work together. Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel, and let's keep these old machines' legacies alive. A model 1855 rifle musket with a broken firing pin couldn't use the firing pin from another model 1855. The lock plate from one rifle wouldn't fit another. Ramrods varied in diameter by thousandths of an inch, jamming in some barrels, rattling loose in others. Barrel bands required individual fitting. Each weapon was technically identical in design, manufactured in the same facility. Yet every component needed hand adjustment by skilled gunsmiths to function in a different rifle. The Confederacy had captured thousands of weapons and couldn't make them operational without machinists they didn't have. This wasn't a Confederate problem. It was an American problem. Across the North and South, the entire manufacturing system operated on a fiction. Factories claimed to produce interchangeable parts. They advertised standardized production. The reality was hand-fitting, filing, adjusting. 2 rifles from Springfield Armory, same model, same year, manufactured in consecutive months, had incompatible parts. A government study in the 1840s documented interchange failure rates between 40 and 60%. What manufacturers called precision was guesswork dressed in calipers and eyeballing. Every American workshop faced the same limitation. Parts were made to approximate dimensions, then forced to fit during assembly. Skilled fitters spent hours per rifle making components work together. The gun would function perfectly, but disassemble it, mix the parts with another identical rifle, and neither weapon could be reassembled without extensive reworking. This wasn't manufacturing. It was elaborate craftsmanship pretending to be industry. But 3,000 miles away in Manchester, England, a self-taught mechanic had already solved the problem America couldn't see. Joseph Whitworth created measurement standards accurate to 100,000th of an inch. By the 1850s, British workshops manufactured to tolerances American factories couldn't measure, couldn't verify, couldn't reproduce. Whitworth built machines that didn't just make parts, they forced accuracy into existence through principles American industry had rejected. The irony was profound. America invented the concept of interchangeable parts. Eli Whitney demonstrated musket assembly from random components in 1801. The American system of manufactures became a point of national pride. But it was Britain that made interchangeable parts actually work, and an English engineer who created the standards that would eventually build the arsenal of democracy. This is the documented story of how Joseph Whitworth developed precision measurement when America had none. How his innovations transformed manufacturing despite American resistance, and how that obscure achievement in metrology won wars through the simple act of making things fit together. Joseph Whitworth was born December 21, 1803 in Stockport, Cheshire. His father served as both schoolmaster and congregational minister, a position that provided respectability but little money. At 14, Whitworth left formal education to work in his uncle's cotton mill, learning practical mechanics among the looms and power transmission systems that drove Britain's industrial expansion. The textile machinery required constant adjustment, repair, improvisation. Whitworth absorbed the rhythm of industrial problem-solving, the gap between design intent and manufacturing reality. At 19, he moved to Manchester and apprenticed to a toolmaker. The work was precision-focused by 1820 standards, meaning accurate to within a few thousandths of an inch on good days. But the crucial decision came in 1825 when Whitworth relocated to London to work for Henry Maudslay, the man who would reshape his understanding of what precision meant. Henry Maudslay had invented the first bench micrometer in 1805, a measuring instrument accurate to 1/10,000th of an inch. This wasn't theoretical capability. Maudslay's micrometer actually achieved repeatable measurements at that tolerance, something no previous instrument could claim. But Maudslay's deeper obsession went beyond measurement. His workshop philosophy reduced to a single principle. First, get a true plane. Every accurate measurement, every precise part, every reliable machine depended on having reference surfaces that were genuinely flat, not approximately flat, not flat enough for practical purposes, geometrically true. American workshops in the same era relied on calipers, visual inspection, and the skilled touch of experienced machinists. If a part looked right and felt right, it was right. Maudslay demanded proof. Whitworth spent years in that environment, learning that manufacturing precision wasn't about craftsmanship or experience. It was about measurable, repeatable, verifiable accuracy. In 1833, Whitworth returned to Manchester and opened his own workshop. By 1840, he had patented his true plane method, a breakthrough that solved Maudslay's foundational problem. The technique used 3 metal plates scraped against each other in rotation. Each plate was worked against the other 2, material removed where high spots made contact. The geometry was self-correcting. Only one configuration produces 3 mutually perfect planes, and the method converges on that solution naturally. It required no external reference, no master standard to copy. The process generated truth from iteration. This solved the central paradox of precision measurement. You can't measure accuracy without an accurate reference, but you can't create an accurate reference without the ability to measure accuracy. Whitworth's 3-plate method broke the circle. By 1845, his workshop was producing measuring machines accurate to 1/millionth of an inch. A human hair measures approximately 75 millionths of an inch in diameter. Whitworth could measure differences 75 times smaller than a hair's width, and his machines delivered that precision repeatedly, verifiably in production use, rather than laboratory demonstration. By 1840, Britain faced a problem Whitworth's measuring machines couldn't solve alone. Every manufacturer made different screw threads. A bolt that fit a nut from one workshop wouldn't fit a nut of identical diameter from another maker. Sometimes bolts wouldn't even fit nuts from the same manufacturer, produced in different batches. The railway industry was paralyzed by the chaos. Locomotives broke down hundreds of miles from repair facilities, and replacement bolts didn't fit. Engineers carried files to reshape threads on site. The steamship industry suffered worse. Saltwater corrosion meant frequent part replacement, but ships at sea discovered their spare bolts were useless. The military faced the same crisis. Artillery pieces used custom threads unique to each manufacturer. Rifles required threads cut specifically for each weapon. An 1841 survey by the British Association documented the scope of the disaster. 47 different thread standards were in common use across Britain. Thread angles ranged from 47 degrees to 60 degrees, with no consistency in pitch, depth, or profile. Whitworth began collecting screw samples from workshops across the country. He measured hundreds of threads, documenting the variations with his precision instruments. Thread angles scattered across a 13-degree range. Pitch specifications existed only as rough guidelines. Even within single manufacturers, threads varied batch to batch depending on which machinist cut them and what kind of day he was having. Whitworth concluded that industry needed standardization based on what actually worked, not what tradition dictated. He performed load testing, measuring how much force different thread designs could withstand before stripping. He tested friction characteristics, comparing how much torque different angles required. He measured wear rates under repeated assembly and disassembly. The data pointed to an optimal design, 55-degree angle with specific pitch to diameter ratios and rounded roots and crests to reduce stress concentrations. In 1841, Whitworth presented a paper to the Institution of Civil Engineers titled A Uniform System of Screw Threads. He proposed the 55-degree angle, standardized pitch for each diameter, and published complete tables anyone could use. The standard was open, not proprietary. Any manufacturer could adopt it without paying royalties. But Whitworth included something previous standardization attempts had missed. He specified both dimensions and tolerances. Earlier proposals told manufacturers what size to make threads, but left accuracy to individual workmanship. Whitworth defined exactly how much variation was acceptable, making the standard verifiable with measuring instruments. Railway companies adopted first because economic necessity outweighed pride. Broken locomotives cost money every hour they sat idle. British government military contracts began specifying Whitworth threads in the 1850s. Machine tool builders followed throughout the decade. By 1860, Whitworth's thread had become Britain's unofficial standard. Formal designation as British Standard Whitworth came later, but industry had already voted with orders and specifications. Meanwhile, in America, manufacturers insisted they didn't need British standards. William Sellers wouldn't propose a competing American standard until 1864. But American rifles still jammed from incompatible parts, and American locomotives still broke down from threads that didn't match. In 1851, the Crystal Palace exhibition opened in London, showcasing industrial achievements from around the world. Whitworth displayed his precision measuring instruments alongside machine tools and standardized components. Queen Victoria toured the exhibits and awarded him a medal for excellence in machinery. American visitors examined the British precision equipment and recognized they couldn't match it. The gap between British measurement capability and American approximation was becoming impossible to ignore, but pride prevented acknowledgement. 3 years later, the British government contracted Whitworth to develop a precision rifle. The Crimean War had exposed weaknesses in British infantry weapons. Russian artillery could engage at ranges where British rifles were useless. Whitworth approached the problem like an engineering challenge rather than a military tradition. He tested every variable systematically: barrel length, rifling twist rate, bullet shape, powder charge, barrel thickness. Each test was documented with measurements. Thousands of shots were fired and recorded with the same rigor he applied to screw threads and measuring machines. The result was revolutionary. Instead of a round bore, Whitworth designed a hexagonal barrel. The six-sided shape created a tighter seal, preventing gas escape around the bullet. He specified fast twist rifling, one complete turn every 20 inches, compared to the standard one turn in 78 inches. The bullet was also hexagonal in cross-section, mechanically fitted to the barrel, rather than relying on friction. These specifications weren't guesses. They emerged from measurable testing and documented results. In 1857, Whitworth demonstrated the rifle's capabilities. It hit targets accurately at 1,000 yards. Standard military rifles of the era were effective to 300 or 400 yards at best. The following year, Queen Victoria witnessed another demonstration and expressed her approval. British sharpshooter units received limited numbers of Whitworth rifles, though the design never achieved mass adoption in Britain. But the rifle found enthusiastic customers across the Atlantic. During the American Civil War, Confederate sharpshooters imported approximately 250 Whitworth rifles through blockade runners. Union soldiers learned to fear the distinctive crack of Whitworth fire. The rifles could kill at distances Union troops considered impossible. In 1864, Union General John Sedgwick was positioned roughly 800 yards from Confederate lines at Spotsylvania Courthouse. When his officers suggested taking cover from sharpshooters, Sedgwick dismissed the concern. His last words were recorded by witnesses. "They couldn't hit an elephant at this distance." A Whitworth bullet struck him in the face immediately after. He died within minutes. The technological achievement was undeniable. Whitworth had created the most accurate rifle in the world through systematic application of precision manufacturing principles. But each rifle cost 20 pounds compared to 2 pounds for a standard Enfield. The weapons required machining tolerances that most workshops, American or Confederate, simply couldn't achieve. Small numbers were produced for elite units, but precision at this level remained too expensive for mass production. The rifle proved accuracy mattered in warfare, but wars weren't won by expensive custom weapons. They were won by factories producing millions of parts that actually fit together. Eli Whitney's 1801 demonstration before government officials had become American manufacturing legend. He supposedly assembled muskets from bins of randomly selected parts, proving interchangeable manufacture was achievable. The performance convinced Congress to fund armory expansion and established the mythology of the American system of manufactures. But historians examining Whitney's records discovered the demonstration was staged. Parts were pre-selected, hand-fitted beforehand, or Whitney used sleight of hand to swap components. The interchangeability was theater, not manufacturing reality. The myth persisted for decades, while actual production told a different story. Springfield Armory and Harper's Ferry, the premier federal arsenals, produced weapons whose parts wouldn't interchange. John Hall's Rifle Works in the 1820s came closest to genuine interchangeability through obsessive attention to gauging and inspection. But Hall's methods died with him. They weren't systematically adopted across American industry. By the 1840s, every federal arsenal had developed its own dimensions, its own tolerances, its own master gauges, copied by hand from previous handmade masters. Errors accumulated with each generation of copying. American workshops lacked the foundation Whitworth had built in Britain. They had no precision measuring instruments beyond basic calipers. They had no reference standards verified to millionths of an inch. They had no trained inspectors using systematic gauging. Master gauges were made by skilled craftsmen eyeballing dimensions, then copied by other craftsmen eyeballing the copies. Each arsenal produced parts to specifications that existed only in the accumulated experience of individual workers. No two arsenals made compatible components. Parts from the same arsenal produced in different years often wouldn't fit together without adjustment. In 1840s, congressional investigation documented the failure. Federal inspectors tested parts from different arsenals and found them incompatible. They tested parts from identical production runs within single arsenals and found inconsistency. Repair operations required skilled fitters who spent hours filing and adjusting each component. What American manufacturers advertised as standardized mass production was actually elaborate handcraftsmanship on an industrial scale. In 1853, Whitworth toured American factories as part of a British government commission studying manufacturing methods. He visited workshops in New York, Philadelphia, and New England, observing operations and interviewing managers. His published report in 1854 offered measured praise and devastating criticism. He admired American willingness to mechanize and the ingenious labor-saving machinery developed in workshops starved for skilled workers. But he identified the fatal weakness. The want of a universal system of measurement is a serious evil. American manufacturers produced impressive quantities of approximately identical parts that required individual fitting during assembly. Their interchangeable parts weren't interchangeable. Whitworth observed skilled fitters spending entire days making components work together that were supposedly identical. He noted the absence of precision measuring instruments in most workshops. He documented the lack of verified reference standards. American industry operated on approximation, experience, and the assumption that close enough was sufficient. But close enough meant rifles jammed, locomotives broke down, and the 1861 Confederate capture of Harper's Ferry delivered thousands of weapons that couldn't be made operational without machinists the South didn't have. William Sellers, a Philadelphia manufacturer, studied Whitworth's publications and recognized what the British engineer had achieved. In 1864, Sellers proposed an American standard screw thread to the Franklin Institute. The design was deliberately different from Whitworth's 55-degree angle, using 60 degrees instead. Sellers specified flat crests and roots rather than Whitworth's rounded profiles, making the thread simpler to manufacture with American tooling. But Sellers copied Whitworth's crucial insight. He didn't just specify dimensions. He specified tolerances, defining exactly how much variation was acceptable and making the standard verifiable with measuring instruments. The Franklin Institute adopted the Sellers thread as the United States standard. Federal government contracts began specifying Sellers threads in 1868. American pride was satisfied. The nation had its own standard, different from Britain's, proof of industrial independence. But the difference was superficial. Sellers had imported Whitworth's fundamental principle. Precision manufacturing requires specified tolerances, not just target dimensions. Through the 1870s and 80s, American arsenals finally implemented systematic gauging based on Whitworth's methods. Springfield Armory installed inspection stations where every part was measured against go-no-go gauges. Master gauges were maintained to tolerances Whitworth would have recognized, verified with precision instruments built on principles Whitworth had developed. Workers who previously eyeballed fits now had objective standards. Parts that failed gauge inspection were rejected before assembly, not forced to fit during it. By the 1890s, American rifles achieved genuine parts interchangeability 90 years after Eli Whitney's staged demonstration. American machine tool builders absorbed Whitworth's precision philosophy even while rejecting his thread standard. Brown and Sharp in Providence, Rhode Island began producing precision measuring instruments to compete with British imports. Pratt and Whitney built their reputation on accuracy and standardization. By 1900, American precision manufacturing had caught up to British capabilities. The methods were Whitworth's, even if the standards carried American names. World War I proved the transformation. American factories produced millions of rifles with parts that genuinely interchanged between manufacturers. Repair operations could swap components without filing or fitting. The industrial mobilization that made America the arsenal of democracy in World War II depended entirely on precision manufacturing and verified standards. Every tank, aircraft, and ship was assembled from components made by different suppliers in different states, all fitting together because tolerances were specified and measured. The physics Whitworth exploited in 1840 remained unchanged a century later. Reference standards eliminate accumulated error from hand copying. Specified tolerances create predictable fits between components. Systematic gauging catches manufacturing errors before assembly. Modern production still uses these principles. ISO metric threads adopted in 1947 represent the international version of Whitworth's vision. Every bolt, screw, bearing, and gear manufactured anywhere in the world follows standardized tolerances descended from his work. CNC machining centers achieve accuracy to 1/10,000th of an inch, the same tolerance Whitworth's measuring machines delivered in the 1840s. The three-plate method for producing true planes is still taught in metrology courses. Coordinate measuring machines used in modern quality control operate on principles Whitworth established. Global supply chains, where parts made in different countries assemble into finished products, exist only because standards define what precision means. America rejected British standards in the 1840s and 50s out of national pride, developed its own deliberately different standard in 1864, but adopted every underlying principle Whitworth had proven. Whitworth never patented his screw thread standard. He published the specifications freely, gave them to industry without demanding royalties. That generosity enabled the Industrial Revolution's expansion. He died in 1887, knighted and wealthy, honored for contributions to engineering. But his real legacy was larger than recognition or fortune. Every precisely manufactured object in the modern world, every component that fits exactly as designed, every standard that makes global manufacturing possible, traces back to a self-taught mechanic in Manchester who understood that first you need a true plane, and then you need to measure whether you actually have one.